stuff to review. And so I want to get the screen share going here, get it set up. Hopefully we can do this quickly. All right. Oh, no, wrong. Let's see. Let's get it in photo. Okay, so I want to review some stuff. So I'm going to start early. This is reviewing stuff from the last lecture. So as you can see here, I'm talking about reviewing the spherical basis. So the outline of this material is that I'm going to tell you what the spherical basis is, just define it, just take it for granted. Then I'll show you an application of it to give you an idea of what it's good for, and then I'll give you the deeper significance of it. So the definition of the spherical basis is just 3 unit vectors, E1, E0, and E-1 that span 3-dimensional space, but they're complex vectors, and they're defined here. As you can see, the E plus 1 is with an overall minus sign of x hat plus y hat over root 2. We take them collectively, write them as E sub q, where q goes from 0 to plus and minus 1. You can see that q is kind of like a magnetic quantum number for a system that has an angular momentum of 1. And in fact, that's indeed the interpretation of it. These unit vectors are orthonormal, but in the complex sense. So EQ star dotted and EQ prime is a Kronecker delta. You can expand an arbitrary vector x as a linear, they're complete also, so you can expand an arbitrary vector x as a linear combination of the starred EQs with coefficients you call x sub q. If you define it that way, then the x sub q is the EQ dotted into x. These are expansion coefficients. At the end of the hour last time, I was in the process of explaining a connection between the spherical basis vectors and the YLMs for L equals 1, Y1M of theta and phi with L equals 1. And you get this by just looking up YLMs. Here they are. Here's the 3 of them, 1, 2, and 1, 0, and minus 1 here. And multiply them by the radius r. And if you just look at the formula for them, you'll see that you get square root of 3 over 4 pi is a common factor. And what's left over is the components of the position vector, like my overall minus x plus iy over root 2 z and minus iy over root 2, just by inspection. However, these things in the parentheses here are the same thing as the spherical basis vectors dotted into the position coordinate of the particle. Yeah, question? Yeah, dotted into x. That's what these things are. So in summary, you can write it like this, is that the radius r times y1q is root 3 over 4 pi times the dot product E at q dotted into x, which is otherwise what I'll call x sub q, following this same notation here for expanding a vector as a linear combination of E at star. So this is a useful result then. And then what we do is, and I started to tell you about this last time, is we apply this to an application of the spherical basis to the evaluating the matrix elements that are needed for radiated transitions between 2 states of a single electron atom, upper state NLM and lower state N prime L prime M prime in a central force model. So these are the matrix elements that are needed for studying the radiated transitions between the upper and lower states. And there's actually quite a few matrix elements that are needed because X has 3 components, and the magnetic quantum numbers M and M prime take on various values as well. These are basically substates of the upper and lower states of the atom, which all have the same energy. Okay, so as I explained last time, this gives rise to quite a large number of matrix elements that need to be evaluated if you want to know, for example, the intensity of the light emitted. I think I spoke of the example of the 3D to 2P transition, and that gave a total of 45 matrix elements if you just multiply out the possibilities there. All right. So the strategy for dealing with this and doing all that work is, first of all, instead of expressing the position vector x in Cartesian components, which is what that x vector means, we'll expand it in terms of the spherical basis, so the components are x sub q. Now, the number of matrix elements is still the same, but this allows us to evaluate this in a convenient way. So I'm going to proceed now with the beginning of tonight's lecture. The rest of that was just review. So we take this matrix element, we just write it out as an integral. So you get an integral from 0 to infinity, right in spherical coordinates, r squared dr, and then an integral over omega. That's the basically takes care of the integral. And then the wave function on the left is rnl of radius r times a ylm of theta and phi. And that has to be complex conjugated because it's on the left-hand side as a bra. Now for the x sub q, what we do is we use the formula that I just quoted for you right here. X sub q is going to be equal to, if I bring the root 3 or 4 pi over to the other side, I can write it in terms of r times y1q. So let me do that. So the x sub q part then becomes the square root of 4 pi over 3 times radius r times y1q of theta and phi. And then finally, the prime state on the right-hand side is r n prime l prime of radius r for the radial wave function times y l prime m prime of theta and phi. Okay, now my papers fell, so I have to, my papers fell. So I have to, where did it go? Excuse me a second here. It's right here. So I'm going to need that later. All right, so let's see. It looks like that's bumped into some junk on the screen there. Okay, there it is. Let me lock this in here to get it focused properly. Better. All right, so let's write this as a radial integral times an angular integral. I'll write it as I r times I omega. The radial integral, if I just pick out the radial parts, there's first of all the integral itself, integral 0 to infinity of r squared dr. This radial wave function rnl of r from the left-hand side. There's a factor of r from the middle here. And then there's an r n prime l prime of r from the state wave function on the right. That's the radial part. The angular part, I'll bring the root 4 pi over 3 out front. We get an integral over solid angle d omega. We get a ylm complex conjugate here. We get a y1q there. And we get a yl prime m prime there. And what you see is that a couple of things is that all of the magnetic quantum numbers that appear in the original matrix elements, which includes not only the m, but also the q there and the m prime, all three of those are now contained in the angular part of the integral. They don't appear in the radial part. And moreover, the integral itself is a product of 3 YLMs, and that's something we can use the 3 YLM formula for that I derived for you at an earlier stage in an earlier lecture. So to remind you what that is, let me put it up a little bit, like so, and I'll put the YLM formula down below. You can see it here. It's an integral of 3 YLMs. The first one is complex conjugated. There's a bunch of square roots, which is like a normalization. And then there's a product of 2 Clebsch-Gordon coefficients, one that has magnetic quantum numbers and then the other one doesn't. And if we apply that to this integral here, then what we get, the 4 pi over 3, it turns out cancels. And we get the square root of 2l prime plus 1 divided by 2l plus 1. And then what's left over is the Clebsch-Gordon coefficients. There's an Lm, and then we can write this as 1 L prime Q M prime. And the scalar product of that, so that Clebsch-Gordon coefficient, and that's multiplied by another one, which is 1. Let me get it right. This is a 1 here. 1 L prime 0 0, and then we have L0 like so. Okay, so that's the angular integral. All right. Now then, so the result of this is that we got an explicit formula for the angular integral, and the dependence on the magnetic quantum numbers is captured by this Clebsch-Gordon coefficient. Here they are, M, Q, and M prime, and they don't appear anywhere else. So what that means is that, for example, the 45 matrix elements we needed for that 3D to 2P transition, the number 45 comes from the different combinations of magnetic quantum numbers. So all 45 matrix elements can be computed by this formula essentially just by looking up Clebsch-Gordon coefficients. So there's really none of those integrals actually need to be done. There is, of course, the radial integral that has to be done, and this trick that I've just outlined for you here doesn't help you do that. But you do the radial integral once, and then all the rest of the integrals are taken care of for you. So
Sorry, I
this,
had a question on the, I guess, the initial theory. So when we're calculating radiative transitions, why do we need that X sandwiched between the NLM states? Aren't we just doing the overlap between states?
no, because there's a perturbation which is inducing the transition between the two states, and this is the electric dipole operator, which is the charge of the electron multiplied times the electron position.
Oh, I see the okay, thanks, the dipole operator.
So that's where it is. This is why these are electric dipole transitions. These are the most intense of the transitions, so you take care of them first. They're the ones that normally give rise to light. I mean, there's others too that have lower intensity by quite a factor. So these are the dominant effects, electric dipole. Now, of course, X is a vector, so what you really have is a vector of matrix elements that ends up getting you form the dot product of that with the polarization vector of the outgoing photon to give you a scalar, and you square that, and that gives you it's proportional to the probability, excuse me. Yeah, when you square it, it's proportional to the probability of a photon going out with a given polarization. That this is how the theory works. Obviously I haven't derived that now, but we'll actually do it next semester and derive it in all detail. You'll see. But I think you may have seen this, at least this matrix element in your undergraduate course, because it's typically covered in such courses.
Yeah, I just forgot that it came from the dipole, but that makes sense. Yeah.
Okay, great. So this is a real practical problem here. And you can see that this trick, namely the 3YLM formula, amounts to a great savings of labor in doing this. It does something else too. It gives you selection rules. That is to say, the original matrix element, being proportional to this Clebsch-Gordon coefficient, obeys the same selection rules as the Clebsch-Gordon coefficient itself. And there's two of those. There's one in the magnetic quantum numbers. It says that this thing is, let me put it on this way, this thing is equal to 0 unless, here are the selection rules. The first one is on the magnetic quantum numbers that M must be equal to Q plus M prime. And the second one is that the L value on the left must belong to the set of L values that can be obtained by combining 1 with L prime on the right. So it's either L prime minus 1, L prime, or L prime plus 1. This is just using the rules for the addition or the combination of angular momenta. But they give us selection rules. And these selection rules are going to tell us that some of those, in this case, 45 matrix elements are actually equal to 0. You can work out what they are, how many there are. There's actually most of them die, but there's still plenty of matrix elements to do. So this turns out to be still quite a labor-saving device to do it this way. All right. Now, in addition to that, these selection rules aren't just tricks for doing the calculation. They have physical significance as well. And the reason is this, is that in our initial state here, before the atom emitted the radiation, the atom is in an angular momentum state with quantum numbers L and M. That means its eigenstates of L squared and LZ, where L and LZ are the total angular momentum of the system. But it makes a transition, and when it does, the angular momentum, the L and M may well change to new numbers, L prime and M prime. In fact, they have to, into new numbers. And the result is that the angular momentum of the atom is not the same as it was in the final state. So the question is, what happened to angular momentum conservation? Is that a fundamental law of nature, or is it not? The answer is that it is a fundamental law of nature, but the extra angular momentum was carried off by the photon that was emitted. Now, a photon is a particle that has spin 1. And what's happening here is that the reason we're getting a 1 here in this combining of angular momenta is because that's the spin of the photon. So the fact that the angular momentum of the initial state is that of the final state plus or minus 1 is a way by using you see in the final state, you've got the angular momentum of the atom, which is L prime. It's crossed with the 1, which is the angular momentum of the photon, to give you these possible values, of the combined angular momenta. And the initial angular momentum has to belong to them, or else the matrix element is 0. Moreover, the M equals Q plus M prime is a way of saying the M and M prime are the LZ, Z component of the angular momenta of the initial and final states. And what that means is that Q here has a physical significance. It's the Z component of angular momentum of the photon. All right, so that's the physics that's behind these selection rules. These are features here enhancing computational effort, decreasing computational effort, and finding selection rules. These are typical applications of the Wigner-Eckart theorem, which I'm going to address later on in this lecture. And in fact, this example is in fact an example of the Wigner-Eckart theorem. All right, so that's the spherical basis. That's an example of what it's good for. Now, the next thing I want to do is to tell you what its deeper significance is. So to do that, I'm going to begin by making a table here. Let me start with a space. By that I mean some kind of a vector space. In the initial space, I'm going to make a big table here. It probably won't fit in one line, but I'll start out like this. Initially, let's start with the vector space I've typically been calling E, which is the ket space or the state space for a system. And let's look at what the action of rotation operators on this space, the action of SO3 rotations. And that is that the state vector psi gets mapped into U times psi. I'll write it like that. And let me mention somewhere that what the U means is the U means U of n hat comma theta, and it corresponds to a classical rotation R that has the same axis and angle. So in this table, that's what that means. Now this rotation has generators, which are the angular momenta, that's the angular momentum operators of the system. It also has a standard angular momentum basis, which I'll call SAMB here, which are eigenstates of J squared and JZ. We call these gamma JM in a general notation like that. And I want to continue this table down below. And so let's look at the action. The last entry is the action of the rotations on the standard angular momentum basis. And by that, what I mean is we apply U to a gamma JM. And what do we get? We get the sum on M prime of gamma JM prime times the D matrix DJ M prime M, which is parameterized by the unitary operator U, like so. This also has the same axis and angle. All right, so this is the action of rotations on state spaces. Now, the same analysis, the same mathematical analysis can be applied whenever rotations act on any vector space. It doesn't have to be a space of ket vectors. A nice example is ordinary three-dimensional space, three-dimensional physical space, three-dimensional physical space. Rotations act, this group SO3 acts in ordinary three-dimensional space just by these rotation matrices we're talking about. So a vector X gets mapped into R times X. These rotation matrices are orthogonal and therefore unitary. So it's unitary operators on ordinary three-dimensional space. What are the generators? Let's talk about the generators. For that, I get a new piece of paper here. The generators, by what we mean by the generators, is that U of R should be equal to, let me just write as U of n hat comma theta is equal to E to the minus I theta times n hat dotted into J. And I'm going to find it convenient for this immediate discussion to set H bar equals to 1 to simplify the notation a little bit. So if I think of R of n hat comma theta in the same way, we know what R is. This is equal to E to the theta times n hat dotted into these script J vectors, which a vector of 3x3 matrices we introduced when talking about classical rotations. So there's a script J. This is how I'm writing when I do it by hand. And in the typed up notes, I've got different fonts and tech fonts and stuff. But the point is this script J is a vector of 3x3 matrices, which is supposed to be notationally different from that Roman J, capital J, which is the operators. But we make them look the same if we write script J is equal to I, sorry. Make them look the same if we write Roman J is equal to I times script J. And if we do that, then we get J1. J1, the first matrix is this. It's 0, 0, 0, 0, 0, minus I, 0, I, 0. We have a J2, which is equal to 0, 0, I, 0, 0, 0, minus I, 0, 0. And we have a J3, which is equal to 0 minus I, 0, I, 0, I, that's an I, 0, 0, and 0, 0, 0 here like this. And if you take these three J matrices, you'll find they satisfy the standard angular momentum commutation relations. So following the mathematical notation here, the generators here are I times these script J matrices. Now what's the standard angular momentum basis in ordinary three-dimensional space? Well, let's play some games with that. So in the first place, whatever it is, let's call the standard angular minimum basis, of course, is going to have it's going to be an eigenstate of j squared and jz, right? So let's calculate, what is j squared? Well, j squared is the sum of the squares of these three matrices. If you do the algebra and add them up, here's what you get. You get 2, 2, 2 in the diagonal and zeros in the off diagonal. In other words, it's equal to 2 times the identity matrix, like this. Now, what this means is that every vector of three-dimensional space is automatically an eigenstate of j squared with an eigenvalue which is equal to 2. But the eigenvalues of j squared are j times j plus 1. And j times j plus 1 equals 2 if j is equal to 1. And if j is equal to 1, we get a three-dimensional space because the magnetic quantum number can go from -1 to +1. So what we're seeing is that ordinary three-dimensional space actually is a single irreducible subspace under rotations with an angular minimum value of j equals 1. We know it's 3D. All right. What about the vectors themselves? Let's look at the stretch vector. Let's just call it E1, give it a notation. What do we know about it? Well, we know that Jz acting on it has to give you an eigenvalue of 1 times E1, right? So let's work it out. Here's the Jz right there, J3. So we get 0 minus I0, I0, 0, 0, 0, 0. Let's call the vector X, Y, and Z, like so. And we set this equal to X, Y, and Z because it's supposed to be reproduced by the Jz. Multiplying this out, you see this gives you Iy is equal to X. It gives you, excuse me, it's minus Iy equals X. I'm multiplying the first row and the first column. Then you get Ix is equal to Y. And the last one gives you 0 is equal to Z. And so the vector E1 then is equal to, if I set X equals to 1, then Y is equal to I and Z is equal to 0. That's not normalized. If I normalize it, I divide by the square root of 2. And I'm going to put in a conventional phase factor of -1 for reasons I'll explain in a minute. And if I do that, I get a unit vector. And lo and behold, it is the spherical basis vector for Q equals +1. Now I'll leave it as an exercise for you to apply J minus operators using these three J's to that vector. And if you do, you'll generate E0 is equal to Z hat and E minus 1 is equal to 1 over root 2 times 1 minus I and 0. And thereby we generate the spherical basis. So the spherical basis is the standard angular minimum basis in ordinary three-dimensional space. We chose the phase -1, which as far as the theory of angular minimum is concerned is just an arbitrary phase. We chose the phase -1 for the stretch state in order to make the middle one turn out to be Z. That's just a convention. But if we do this, and we can now start to fill in our table here, is that the standard angular minimum basis here is equal to the E hat sub Q's. And how do they transform under rotations? Well, the E hat sub Q, if I apply rotation to it, it's just rotating the vector, that's all it is. And this has got to be equal to a sum on Q prime of E hat Q prime times D1 of Q prime Q of the corresponding rotation R, like this. This is how the spherical basis vectors transform when they're rotated. Now, this is not a formula I have to prove because it's really just a version of the formula immediately above it. Once we grant the formula above it, then this one follows immediately also. The reason is it's just a change of notation. That's all we've done. All the mathematics we did in deriving the earlier transformation formula and speaking about Ket spaces applies equally well to what we're doing in ordinary three-dimensional space. We got eigenstates of J squared and Jz, and we use standard raising and lowering operators. So this has to be true. Okay. So as I said, just mentioned, it's really just a special case of the upper formula with a reinterpretation of what the vector space is. Okay, this final result has some interesting consequences, which I'd like to flip over to another page and tell you about. So let me do that. Get rid of the pages I don't need anymore. And so here's the story. Let's do it this way. Let's get this on the screen. Let me give you some no, I want to save this page. Let me get it on a new piece of paper. I want to show you some consequences of this formula. Let's take this and let's form a dot product of E hat sub Q complex conjugate, Q prime complex conjugate on both sides of this equation. On the left-hand side, let me show the dot product like this with little roundy brackets. E hat sub q star, comma, r acting on E hat sub q. On the right-hand side, because of the orthonormality, you're going to pick out the one term in this expression on the right-hand side, the one coefficient, which is the D matrix. It's D1 Q prime Q, Q prime Q of R. And what you can see is that the D1 matrix for the value j equals 1 is actually the matrix elements of the classical rotation matrix with respect to the spherical basis. This should have been a prime here, Q prime on the left, Q prime Q, Q prime Q. All right. If we took the matrix elements of the rotation operator with respect to the Cartesian basis, C hat I, comma, R acting on C hat J, where the Cartesian basis is just X hat Y at Z hat, then this gives us Rij, which is the usual matrix that we think about in talking about rotation matrices. And so what we see is that D1 is obtained from the classical rotation matrix by changing the basis from the Cartesian to the spherical basis. It's just a unitary transformation of basis. All right. So those are some consequences of that. All right, now then. In the next stage, let's go back to our table here of vector spaces on which rotations act. Let's generalize it even more. Let's talk about spaces of operators. Operators, I mean the operators that act on a quantum mechanical system. They form a vector space because you can add them and multiply them by scalars. If A is such an operator, how does it transform under rotations? We just showed you what that was, or I did in the last lecture. Let me write it correctly. It is U dagger. You just basically conjugate the operator by the unitary rotation operator, and this is how what we regard as the rotated operator. Now this has certain generators, which I'm not going to fill in tonight. I'll leave it as an exercise for you to think about what they are. What about the basis of standard angular minimum basis? What are they? Well, a standard angular minimum basis would be a collection of operators which transformed in a certain way under rotations. Here's the notation that's used for that. The notation is this. As we talk about operators, I write like this is TKQ. Actually, it's a collection of operators. TKQ, where Q runs from minus K up to plus K. This is a collection of 2K plus 1 operators. And the idea is that K plays the role of it's like a J value in an angular momentum theory. And the Q index down below is like a magnetic quantum number M in angular momentum theory. So we speak about this is an object which, by the way, is called an irreducible tensor operator. Irreducible, I can spell it here. Irreducible tensor operator. So an irreducible tensor operator, I'll define it in the next few sentences. An irreducible tensor operator in the first place is a collection of 2K plus 1 operators, where the upper index is considered fixed and the lower index is variable. It runs over a total of 2K plus 1 values. These are considered to be the components of the irreducible tensor operator. The K index that occurs here is called the order of the operator. So the operator has order K, then there's 2K plus 1 components. And what qualifies it as an irreducible tensor operator is how it transforms under rotations. And the transformation law is this, is that if I take one of the components, TKQ, of this collection of operators and rotate it, which by our rule means you just conjugate the rotations, this gives us a sum on Q prime of TKQ prime times the D matrix with an upper index of K, components QQ prime, parameterized by the rotation U like this. In other words, it transforms as a standard angular momentum basis in any vector space. And so back up in this table here, we'll put a TKQ here for the standard angular momentum basis. And so to recapitulate slightly, an irreducible tensor operator of order K is a collection of 2K plus 1 operators that transform into rotations in this manner. Now, what this means is that if we take any one of the components of an irreducible tensor operator and we rotate it, what we get is a linear combination of the other 2k+1 components in which the coefficients are given by the D matrices. I can make a similar statement about the basis vectors of the Ket, the standard angular minimum basis vectors of the Ket space, or the other example as well. But what that means is that the space of operators which is spanned by the components of an irreducible tensor operator is an invariant subspace of operators under rotations. And as it turns out, as the name would suggest, it's also irreducible, which means it doesn't have any smaller invariant subspaces. In any case, this is the definition. And I want to draw your attention between the definition here and the properties of these other objects transforming under rotations. Okay. Now, that's the definition, maybe a little bit of motivation for an irreducible tensor operator. Now let's get some examples of them. The simplest example is an irreducible tensor operator of order 0, k equals 0. If k is equal to 0, then the corresponding magnetic quantum number, which we call q, is also equal to 0. So in this case, the irreducible tensor operator has only one component, t0, 0. And if I conjugate it by rotations, gives us the rotated operator. This is going to be equal to a sum on q prime of t0 q prime times d0 q prime. Q prime, well, it's got to be 0 by the formula that we used. However, the q prime index can only take on the one value 0. If k is equal to 0, q prime is equal to 0. So this has only one term. It's t0, 0 times d0, 0 of the rotation u. Now, perhaps you remember that the D matrices, when the angular momentum J is equal to 0, consists of just the 1-by-1 matrix containing 1. And that's because states that have 0 angular momentum of whatever kind, whether it's orbital spin or anything else, they're invariant under rotations. Now, these are not states, these are operators. But nevertheless, if the angular momentum quantum number, which we call K here, is 0, it means it's invariant under rotations. So this just becomes T0, 0. The D matrix has to be just 1-by-1 matrix containing 1. So what you see is that this T0, 0 operator is invariant under rotations, and that means it's a scalar operator, which are previously called K, like this. So K equals 0 means a scalar operator. Scalar operators are irreducible tensor operators of order 0. And this applies, I'll remind you, in particular to the Hamiltonians for any isolated system. What about k equals 1? Let's look at those. Turns out that k equals 1 irreducible tensor operators are the same thing as vector operators, but with their components put into the spherical basis. I'll show you how I know that. Let's say that v vector is a vector operator. And then let's take that v sub q is equal to e hat q dotted into v. Now then let's conjugate vq by rotations. We rotate one of the components of this v sub q. What does this give us? It gives us e hat sub q dotted into u v vector u dagger, like this. But this is now in Cartesian components. And so this is e hat sub q dotted into r inverse multiplying v by the transformation law of the Cartesian components of a vector operator. That was the definition of a vector operator. Now in this expression, I can move the r over to the other side of the dot product, but I have to change it from an inverse into just an ordinary r. That was a homework problem, and I think you maybe remember that. So we can write it like this. And being a dot product, I can write it in either order. I can write it as v dotted into e dotted into r times e hat sub q. Let's do it that way. And that's the same thing as v dotted into, actually you got to be careful with rearranging dot products because operators don't commute. But the v is an operator and the r times e hat sub q is just c numbers. So in this case, it's okay to reverse the order. In any case, this becomes v dotted into, but now r and eq, we know what happens to that because we got our table of transformation properties. Here it is. That's how the spherical basis transforms. So this becomes a sum on q prime of v sub e hat sub q prime times d1 of q prime q of u, like so. And now the v hat dotted in eq prime, it's sum on q prime of v sub q prime times d1 of q prime q of u. And so what we see is that conjugating component of v hat sub q gives us exactly what we need for an irreducible tensor operator of k equals 1, because that's the one that appears here in the D matrix. So any vector operator just transformed into the spherical basis gives us a k equals 1 irreducible tensor operator. That's what we did earlier with the position operator of the electron, to convert that, the operator whose matrix elements we were looking for the transition probability for radiated transitions, in order to put that in a form where we could use the 3YLM formula. All right. So in other words, what it gave us ultimately was the matrix elements of a k equals 1 irreducible tensor operator with respect to a standard angular momentum basis, which for our atom was the NLM on one side and the NLM primes on the other side. That's initial and final states. Those are standard angular momentum basis factors, which are also happen to be energy eigenstates. But that's a normal eigenbasis we use for single electron atoms, and is what naturally emerges in the theory of emission and absorption of radiation. So that's an example where we end up with matrix elements of irreducible tensor operators with respect to standard angular momentum bases. This is a more general case. What about k equals 2? Is there an example of that? A second order irreducible tensor operator. Let me say some things about that. The simplest example of a k equals 2, bring down so you can see it. Simplest example of a k equals 2 irreducible tensor operator is a quadrupole moment operator. It was given in Cartesian form earlier. It looks like this. If I have a collection of particles that I index by alpha, it's a sum on alpha of the charges q alpha, and then we multiply by 3x alpha I times x alpha j, the I and j components of particle alpha multiplied together, minus r alpha squared times delta ij. That's just the definition of it. Now this is a tensor operator in Cartesian form. I used a general notation Tij for them previously, and this consists of 9 operators, the components of the Tij. But as I explained, that space span of operators spanned by those components, that 9-dimensional space, is reducible. It breaks up into a 1 and then into a 3 and then into a 5. These are the dimensions that I'm giving here: 1 plus 3 plus 5, so that the total makes 9. The 1 is the trace of T, and the 3 is the antisymmetric part, and the 5 is the symmetric and traceless part. The quadrupole moment tensor, however, is traceless. That's what subtracting off this delta ij does. If I take the trace of x alpha I, x alpha j, what I get is I just get r alpha squared. If I take the trace of Kronecker delta, I get 3. So that's where the 3 comes from. It's cooked up to make this thing traceless. So the 1 does not contribute. Also, the 3 here for an arbitrary Cartesian tensor was the antisymmetric part. But this Qij is symmetric, so it doesn't have the 3 either. So even though this Qij has 9 components, actually only 5 of them are independent. And those 5, if you form linear combinations of them, you can rearrange them. So the Qijs, by forming linear combinations, you can rearrange them to create what, let me call it k sub 2q like this, where q runs from -2 up to +2. There's some coefficients you need to work out to do this. And if you do, you end up with a second order irreducible tensor operator. It would transform this way: is that u q2q u dagger is equal to the sum on q prime of q2q prime d2 q prime q of u. It would rotate this way using the j equals 2 matrix for rotations. Okay. So those are then 3 examples of irreducible tensor operators of various orders, and also some examples of how they get applied in practice.
I have a question. I thought in the last lecture, we only proved that tensor operators were reducible if they were written as a form times VI times WJ.
If they're only irreducible if they're written how?
If they're written as the outer product of 2 vector operators.
No, that was the scalar part, or the trace. The trace, if T is equal to VI times WJ, that's a special form of such a tensor. And then the trace of it is the dot product, and that's the part which is the k equals 0 part. It's the scalar part. Dot product is a scalar.
Okay.
But there are other parts as well. There's three components that are taken up by the antisymmetric part of it, of the tensor, which if this were a VI times WJ, that's the cross product of the two vectors, which is a vector. And
Right.
therefore, as we've seen, is a K equals 1 irreducible tensor operator.
But I guess I thought, but we made that decomposition using the fact that this tensor was an outer product operator, but that's not generally the case.
We
for a
took that
tensor.
as an example, and it illustrates the decomposition, and it makes it plausible. You can see why the middle
Oh.
one has three components and is also a K equals 1.
But it's always true.
Same decomposition works for any
Okay.
any operator. And by the way, the quadrupole moment tensor operator has such an outer product you see right here. It's the outer product of the charged particle, the position operator for the charged particle times itself.
Oh, yes, of course. Sorry. Yeah.
See that? And the R alpha squared here is the trace of that.
Yes.
Okay.
Okay. Sorry. Thank you.
Yep. So the quadrupole moment tensor is actually a linear combination of such outer products. And more generally, any as a practical matter, any second rank tensor, irreducible tensor operator that you're going to find can or any Cartesian tensor can be represented as such outer products. This is a linear combination of such things. All right. Okay. So anyway, the quadrupole moment tensor is probably the prime example of a K equals 2 or second order irreducible tensor operator. Yes, go ahead.
So in order to be the standard angular momentum basis for the operators, we need it to be traceless and symmetric, right? Because then we have
no. That's if you want to get the K equals 2 part of the Cartesian tensor. The Cartesian tensor is reducible, and it breaks into 3 irreducible parts. One is a scalar K equals 0, one is a vector K equals 1, and the last one is the K equals 2. The quadrupole moment tensor belongs only to the K equals 2 part, because if you look at the formula for it, you can see that it's symmetric and traceless.
Oh, I see. Okay, I see.
Yep. Okay. In other circumstances, these other parts might play a role. In fact, they do. By the way, just to mention again, physical applications, the quadrupole moment tensor is used to find the energy shift, or it's really the Hamiltonian giving the energy shift for a charge distribution which has an electric quadrupole moment in the presence of an external electric field. So this applies for example, in the case of a nucleus of an atom, because they're charged particles, i.e. protons inside the nucleus. And in general, they create an electric quadrupole moment. There's also an electric field which comes from the electron cloud, or maybe the chemical environment of the atom in a solid or a molecule. And so there's an energy that's associated with the orientation of that nucleus in that external field, and that gives rise to it's usually a perturbing Hamiltonian called delta H or something, but it involves the relationship between this Qij tensor and the external electric field. So now when you're going to do perturbation theory and find out what are the energy shifts due to that, so that I can measure it and so on, you can see that once again, what you're getting is matrix elements of irreducible tensor operators with respect to standard angular momentum bases. It's rather similar to those matrix elements for radiated transitions, but it's a different application, perturbation theory, and more complicated because it's order 2 now instead of order 1. So I'm just saying all this because to point out that that's a physical application of this, and also to emphasize the fact that matrix elements of this type are extremely common in all areas of quantum physics: atomic, molecular, nuclear, condensed matter, particle physics. It's everywhere. So they're used everywhere. Okay. All right. So so far then, definition of irreducible tensor operators of order K, and several examples of them of order K equals 0, 1, and 2. All right. Now then, also we know how they transform. Now, you may recall that in the case of scalar operators, we called them K, there were 2 definitions of them. One is that if you conjugate it under rotation, the operator is repeated. And the other one was commutation relations with the angular momenta. And these are actually equivalent to one another, and they imply one another. And the second one comes from making the U operators over here infinitesimal, and then you get these commutation relations. So it's kind of like for finite rotations and infinitesimal rotation, commutation relations. That's the way of thinking about them. You can choose either one as the definition of a scalar. And if you look at different books, they might do it different ways, but they're equivalent to each other. Now for a vector operator, we did it in Cartesian components. It was this: uv vector u dagger is equal to r inverse times u times v. That was our definition of a vector operator in Cartesian components. But we found also that there was a commutation relations, and it was ji, let me get it right, ji vj commutator. That's supposed to be a vj there. Let me put it down below just to make it clear. Is equal to I times epsilon ijk times v sub k here. There's really an IH bar. I'll set h bar equals to 1 for most of what I'm doing tonight because it saves writing. In any case, these are the commutation relations for the Cartesian components of a vector operator. All right, and we can do something similar for tensor operators, which I won't bother to write down. Now, for irreducible tensor operators, TKQ, we've got a definition in terms of finite rotations. It's this: u TKQ u dagger is equal to the sum on q prime of TKQ prime times DK Q prime Q of U. And I'm just copying the formula that I wrote down earlier in my table of transformation properties, but that's what this is. It's like these finite rotation transformation properties that we saw before for scalars and vectors. Now the question is, does that correspond also to some version of infinitesimal commutation relations? And the answer is yes. And it turns out there's 3 of them. There's 3 or 4 of them, which I'm going to leave some space here to fill in down below here. So let me save this sheet of paper and we'll work on them. So the way to do this is to specialize to infinitesimal rotations, just as you might expect. That's the way to get this. Let me get this page right here, straightened out. And okay. So here's what we'll do. Let's let the rotation be infinitesimal. That means that u is equal to 1 minus I theta times n hat dotted into j. I'm setting h bar equals to 1. So if I take my formula here and I look to the left-hand side is going to be equal to 1 minus I theta n hat dotted into j. That's the u part right there, times the TKQ. And then the u dagger is 1 plus I theta times n hat dotted into j. And then the right-hand side is this sum over here. So that's going to be the right-hand side is the sum on q prime of TKQ prime. And now what I have is the DK Q prime Q of u, but I want to make that u infinitesimal. Let me fill this in later. Let me make a little digression here. The DK Q prime Q of u, let me write it this way as a scalar product of KQ with u KQ prime. Because the D matrices are the matrix elements of the unitary rotation operators. And so if I use that notation here, then I've got a KQ. This should be, I'm sorry, the primes and unprime got reversed here. Q prime is the first index and Q is the second one. This is KQ prime, 1 minus I theta times n hat dotted into j. That's for the u in the middle. And then the KQ on the other side. All right, so this left-hand side and right-hand side are supposed to be equal to one another. Okay. Now, I have to explain, before proceeding with this, I have to explain something, which may be a little confusing for you, but let me try to explain as best I can. And that is that the J operator that appears here on the right-hand side is actually not the same as it is on the left-hand side, or it need not be the same. The reason is this. The original definition we gave of the D matrices was this. If you go back to the lecture notes, it's DJMM prime of U is equal to JM on the left, U of the rotation operator U in the middle, and JM prime on the right. It's just the matrix elements of the rotation operator is all it is. That's what the D matrices are. But the question is, in what space do these vectors JM and JM prime live? Originally, when we did this, we were thinking about a space in which J squared and JZ were complete by themselves, so we didn't need any extra gamma index. That's why there's none appearing here. the fact is that it doesn't matter what space that this is in, because the derivation of the D matrices, the definition of them, didn't depend on anything at all except for the existence of the angular momentum operator and its commutation relations, as well as phase conventions we made for the standard angular momentum basis. That means we use the standard raising and lowering operator formulas. And if we do that, we're going to get the D matrices. The numbers that come out are going to be the same for all possible realizations of that angular momentum operator. In other words, it applies to orbital spin. It applies to all these other cases as well, three-dimensional space, operator space, everything. It applies to any mathematical vector space upon which rotations act. It's completely independent of the physical nature of the system and is really a property of the rotation group plus some conventions that we use. And so when I want to talk about the D matrices and I need to use them, I can, if I like, think about constructing some kind of, instead of letting the vectors of this scalar product be the space that I'm working in, like my atom or something, I can let it be the vectors of a model space, which is just set up for the purposes of constructing the D matrices. And that's the right way to think about this DKQQ prime. Here, we just set up some model space with vectors KQ. That's the basis vectors in that space. By the way, the same thing applies to the Clebsch-Gordon coefficients. Clebsch-Gordon coefficients, my notation for them is to write them as a scalar product. Jm on one side, J1, J2, M1, M2 on the other side. But what space is that scalar product taken in? And why don't I have a gamma index in there as well, in case there's degeneracies? J squared and Jz aren't by themselves a complete set. The answer is that it doesn't matter. Is that the Clebsch-Gordon coefficients are again, they're universal numbers that apply in any spaces in which we're combining, two angular momenta, J1 and J2, and picking out the total J's of the result. The calculation didn't depend in any way whatsoever on any of the properties of the space in question, except for the existence of angular momenta and the conventions. So both the D matrices and the Clebsch-Gordon coefficients, you can think of those scalar products or matrix elements as taking place in a model space. All right, with that understanding here, let's take this J that appears here, or n hat.j, and let's replace it by n hat.k, where k vector is the angular momentum in whatever model space we're using there. Let's just do it that way. All right. Now, having done that, let's take this left-hand side and write it out in more completely. The 1 times the TKQ times the 1 just gives us a TKQ. And then the first correction term is going to be minus I theta times the commutator of n hat dot j with the TKQ. That's the left-hand side, because you get n hat j times TKQ, and then with a minus sign, and then with a plus sign, TKQ times n hat dot j. That's this commutator. That's carried out to first order. On the right-hand side, the 1 here gives me the scalar product of KQ prime times KQ. That's a Kronecker delta. So the sum on Q prime can be done, and we just get a TKQ for that leading term. Then the correction term has got a minus I theta comes out. And then what we've got is the sum on Q prime of TKQ prime times the matrix element KQ prime on the left. We've got n hat dotted into our vector K on the right, and then KQ, okay? And these two are equal, like this, okay? Now then, having done that, we can cancel the leading terms, obviously. What's left over, we can cancel the minus I thetas. And the n hat's an arbitrary unit vector, so we can cancel that as well. And what we get is the following, is the commutator of J vector with a component of an irreducible tensor operator is equal to the sum on Q prime of TKQ prime times the matrix element KQ prime, K vector, KQ. Let me box that because that's a useful result. It's basically a commutation relation that's derived from the transformation law of irreducible tensor operators, repeated right there, but one that one gets in the case in which the rotations are infinitesimal. Now let's work on this a little bit more. Let's dot both sides of this with z hat. That'll give us jz here, as you can see, on the left-hand side. It'll give us a kz over there. The matrix element KQ prime, KZ in the middle, KQ on the right. can be evaluated because KQ is an eigenstate of KZ with eigenvalue Q. So KZ acts and then just brings out the Q quantum number. What's left over is a Kronecker delta. This becomes Q times delta QQ prime, like so. That allows us to do the sum. And the result is that we obtain a formula, which I'll put right down here, is that JZ commutator with a TKQ gives us Q times TKQ. It's a special case of this box formula down here. All right. Let me do another one. If we take this box formula down here, instead of dotting by Z hat, let's dot by X hat plus IY hat on both sides. That J vector is going to turn into a raising operator J plus. We're going to commutator J plus with TKQ. Over here, we're going to get a K plus. Well, KQ prime, K plus, KQ is equal to KQ prime times the famous square root K minus Q, K plus Q plus 1 times K comma Q plus 1. And that's equal to Kronecker delta Q prime times comma Q plus 1 times the same square root. This Kronecker delta then allows us to do the TK sum, the Q prime sum here. Q prime gets replaced by Q plus 1. And when you clean that up a little bit, you get a new commutator. Here it is. It's J plus commutator with TKQ is equal to square root K minus Q, K plus Q plus 1 times TK Q plus 1. Likewise with J minus, what you'll find is you get J minus TKQ is equal to the square root of K plus Q times K minus Q plus 1 times TK Q minus 1. And there's yet a similar form, another formula that I won't derive. The derivation is in the notes, but it's of a related form. If I form the sum on I of the iterated commutator of JI with JI with a TKQ like this, what I get is K times K plus 1 TKQ. So these are four formulas which are all basically infinitesimal versions of the transformation property or defining property of the irreducible tensor operators, expressed when the rotation is infinitesimal. And it shows that forming commutators with JZ brings out a Q value, brings out the magnetic quantum number. The analog of that in the case of Ket vectors is that JZ acting on the basis gamma JM just brings out an M. Likewise, commutator with J plus raises the Q index, you see, with the usual square root, except that J and M are replaced by K and Q, which are the analogous quantum numbers for the operator. J minus lowers the Q index. So this moves us up and down amongst the components of an irreducible tensor operator by forming these commutators. And finally, this iterated commutator here is kind of like a J squared operator, it's like a K squared operator. It brings out the KK plus 1 of the order of the irreducible tensor operator. So if you look up irreducible tensor operators, I haven't done it in Wikipedia yet. It's so miserable, Wikipedia, but God knows what you'll find there. But some books, many books would define an irreducible tensor operator as a collection of operators that satisfy these commutation relations. I think maybe Cummins' book does that, rather than the version I gave, which is this single formula up here. But the two are equivalent to one another, and either one will work. Okay. Now, having done all of that, I'm ready to tell you about the Wigner-Eckart theorem, which is what irreducible tensor operators are all about. The Wigner-Eckart theorem concerns matrix elements, which are a very common occurrence in physics, of a standard angular momentum basis vectors, gamma JM, sandwiched around an irreducible tensor operator. We allow the basis vectors to be different, so I'll put primes on one side. We've already seen several examples of such matrix elements, so I don't think I need to motivate this at this point. we'll see lots of them in the course of the course next semester too. This matrix element has quite a few parameters in it. It's got 3 plus 3 or 6 gamma JM quantum numbers, and then 2 more on the operator itself for a total of 8 parameters. 3 of these parameters, the M and the Q and the M prime, are magnetic quantum numbers. And frequently in practice, we need to evaluate these matrix elements for all possible combinations of those magnetic quantum numbers, which can be a big job. It turns out that the dependence of the matrix element on those magnetic quantum numbers is captured by a Clebsch-Gordon coefficient. That's to say that this matrix element is equal to some coefficient here multiplying things times the Clebsch-Gordon coefficient, which is this. It's Jm on the left, scalar product. That's the same Jm you see over here on the left, on the bra on the left. And then we have J prime K and M prime Q, like so. In a standard Clebsch-Gordon coefficient, we'd call it something like J1, J2, M1, M2. You can see the J1 is like the J prime, M prime here for the ket. And what J2 is like the K and the Q of the operator. We kind of reverse the order of them here. The J1 and J2 are like going J prime and KQ. That's just a convention, but reversing them. But the idea is the important thing. The idea is that multiplying this irreducible tensor operator times this basis state has a lot of things in common with multiplying 2 basis states that are irreducible, that are standard angular momentum basis operators, in which we use Clebsch-Gordon coefficients to combine them to get a total angular momentum. That's what's going on here. This is just what's happening. We're combining an angular momentum of J prime with an angular momentum K and picking out a total angular momentum J out of it. The coefficient that appears here depends on all of the parameters of the original matrix elements except for the magnetic quantum numbers. So it depends on gamma and J and K and gamma prime J prime, but not on M, Q, and M prime. So there's a standard notation for this, and I'm going to write it out by repeating the formula gamma JM on the left, TKQ on the right, gamma JM with primes on the TKQ in the middle, and gamma JM with primes on the right. This matrix, this coefficient that depends on everything except the magnetic quantum numbers is written in a form that makes it look like a matrix element. But we omit the magnetic quantum numbers and we put double bars instead of single bars. So we omit the M here, the TK, we omit the Q, put a double bar here, and then we have gamma prime J prime like that. And then the matrix, the Clebsch-Gordon coefficient I just copy, J prime K, M prime Q, like so. And let me box this because this is the Wigner-Eckart theorem. And don't be intimidated by it. It's actually not that hard to use. It's actually quite easy to use, as a matter of fact. There's 2 different applications of it that we can use. But first, let me be clear about the notation. Is that this double barred matrix element here, which by the way is sometimes called a reduced matrix element. This double barred or reduced matrix element is nothing but the proportionality factor between the matrix element of the irreducible tensor operator in a standard angular momentum basis and the Clebsch-Gordon coefficient, which captures the dependence on the magnetic quantum numbers. You could call this coefficient anything you want, use any notation for it that you want. I don't care, but it has to depend on the remaining 5 parameters here, and this is a nice way of writing it. Okay. Now, what is it good for? It's good for 2 things. One is computation. We saw this already in the example of those radiated transitions in the single electron atom. We found using the 3YLM formula that our matrix element was proportional to a Clebsch-Gordon coefficient. And with change in notation, you can see that it fits exactly the form of the Wigner-Eckart theorem. Although, in fact, the 3YLM formula gives us an explicit expression for the reduced matrix element. We didn't call it that, but it's there. You can look at it and see. So in other words, in some cases, we have analytic formulas for the reduced matrix element. Now, all the things that we did or that I discussed about the computational advantages of that trick appear here in the general case. So, for example, if you know what the reduced matrix element is. Maybe you got a formula for it. Then to obtain all these matrix elements for all the combinations of magnetic quantum numbers, all you have to do is look up Clebsch-Gordon coefficients, number one. Now, in some applications, you don't know what the reduced matrix element is because you don't have a theory for it. What do you do then? Well, one thing you can do is you can evaluate this matrix element over here for just one value of M, Q, and M prime. You choose the ones that make it easiest to evaluate the answer. Just do the integral if you have to. Choose values so that the answer is non-zero. Do that. You get the value on the left-hand side for a particular choice of magnetic quantum numbers. Now look up the corresponding Clebsch-Gordon coefficient, divide that into your answer, and now what you know is the overall reduced matrix element. Having gotten that, you can now just look up Clebsch-Gordon coefficient to find all the others. So there might be 45 of these, and you only need to evaluate one to get all of them. So this is another place where the computational aspects are important. The second application, which is actually probably used more in practice than the other two, has to do with selection rules. That is that the matrix element on the left-hand side has the same selection rules as the Clebsch-Gordon coefficient on the right-hand side. Namely, this is equal to 0 unless two things hold. One is the magnetic quantum number selection rule that M here is equal to M prime plus Q. That's what's on the right-hand side. And the second one is that J must belong to the set of numbers, which starts with J prime minus K and goes in integer steps up to J prime plus K. Like that. So these are the selection rules. And in many cases, all you're interested in, you don't even need to evaluate the matrix element. You just want to know when it vanishes. For a lot of problems, that's all you need. So this is a very common application, is this. All right, that's what the Wigner-Eckart theorem is good for. And that's how you use it. Now then, let me say some things about how we prove it. I wish there were a proof of the Wigner-Eckart theorem that didn't take hours to write down, and it wasn't involve a lot of lengthy summations and stuff, or involves more abstract theory than I think is appropriate for this course. The truth is that if you're willing to do the more abstract theory, it's a special case of what's called Schur's lemma, and you may learn about that if you ever study group theory. So anything that doesn't use that more abstract theory, unfortunately, ends up being kind of messy. So I'm just going to outline some of the ideas behind one of the proofs, a common approach. Let's call it an approach to the proof, which is commonly found in textbooks. I think this is how Cummins does it, actually. So it runs something like this. The basic idea is this: that we show that the Wigner-Eckart, that the matrix elements that we're interested in of irreducible tensor operators with respect to standard angular momentum basis vectors, we show that those matrix elements satisfy the same recursion relations as do the Clebsch-Gordon coefficients. So recursion relations allow you to start with some extreme values of the magnetic quantum numbers where you know the answer, and then to apply the recursion relations and you fill in all the rest. If the T's over these matrix elements on the left-hand side satisfy the same recursion relations, then you can do the same thing, except you don't necessarily know the starting value. But whatever starting value you choose, the rest of it's just going to be proportional. That's where the reduced matrix element comes in. That's the starting value, which you may or may not know. But even if you don't know it, you can give a name for it and call it that. Then you end up with a theorem. So this is the approach to the proof of the Wigner-Eckart theorem, which I want to at least outline slightly. So the strategy then is to show that the matrix elements satisfy the same recursion relations as do the Clebsch-Gordon coefficients. How do we do this? Well, I almost have it here. We go back to our commutation relations for infinitesimal rotations. There's 4 of them. I won't use them all. Let's talk about let's say the first 2 of them. Let's take the JZ one. Let's take this JZ commutation relation here, and let's take it and sandwich it on the left-hand side by a gamma JM state vector, and on the right-hand side by a gamma JM state vector, which is primed. That's the idea, both sides of this equation. And later on, I'll do these other equations too. So let's just take the first equation. Let me do it down here. So we've got gamma JM on one side. We've got the commutator. The commutator is JZ with TKQ. So it's JZ times TKQ minus TKQ times JZ. And then I have a gamma JM with primes on it on the right. And that's equal to the right-hand side up here, sandwiched. So that gives me Q times gamma JM TKQ gamma prime J prime M prime, like that on the right. Now on the left, we let this JZ act to the left and it brings out an M, as you can see. We let that JZ act to the right and it brings out an M prime, as you can see. And then what's left over is just the matrix element of the TKQ, same factor in all three terms. So we end up with this is M minus M prime minus Q times our matrix element that we're interested in. Here it is, and I'm writing it out again, is equal to 0. And thus, either this factor vanishes or the matrix element vanishes. But this factor vanishing means that M is equal to M prime plus Q. So you see what we've obtained is a selection rule on this matrix element. We see that it vanishes unless the magnetic quantum numbers obey the magnetic quantum number selection rule, which is the same as that of the Clebsch-Gordon coefficient. Now that doesn't prove that this matrix element is proportional to Clebsch-Gordon coefficient, but it's a step in the right direction. To get there, we need to work now on the J plus equation. Let's do that one. Again, let me sandwich the J plus equation by two vectors of the standard angular momentum basis. Let's do that one. So we're going to get gamma JM, we get a J plus TKQ minus TKQ, J plus, gamma JM with primes on it, is equal to, on the right-hand side, what do we have here? We've got this famous square root and a TKQ plus 1. K, it's K minus Q, I think. Yeah, it's K minus Q, K plus Q plus 1, times gamma JM, I'm running out of space here, TK with a Q plus 1 is a lower index, and then gamma JM primed on the right. Okay, can you see all of that? Now on the left, I'll let the J plus act to the left on the basis factor, which is now a bra. This is a complex conjugated version of J minus acting on the ket. And so the first term here is going to be this. It's going to be square root of J plus M, J minus M plus 1. And then the vector is gamma J comma M minus 1. Here's the TKQ. And then we get the prime gamma JM on the other side. That takes care of this term. Then for the next term, we have a minus sign, and now we let the J plus act to the right here. And we get the square root of J prime minus M prime times J prime plus M prime plus 1. Gamma JM I copy on the left. The TKQ in the middle I copy. And on the right, the M prime value got raised. It's gamma prime J prime comma M prime plus 1. All right. And so these difference of these two terms is equal to that thing there. Now then, if we just change notation and instead of writing J prime and K, we write J1 and J2, what you end up with is a recursion relation for the magnetic quantum number dependence of our matrix elements. And it is the same, exactly the same structure as the recursion relation for the Clebsch-Gordon coefficients, which I've listed out here. This first term here with the square root of J plus M, et cetera, corresponds to this term here where I let the J plus act to the left. That J minus term here will bring it over to the right-hand side to give us two terms with plus signs. And that's what these two things are. If you just call it, instead of J1, M1, you call it J prime and M prime. And instead of J2, M2, you call it K and Q. you'll reproduce the same formulas. So that's the proof that the matrix elements not only have the same selection, magnetic quantum number selection rule anyway, as the Clebsch-Gordon coefficient, they have the same recursion relations also. And so, as I explained, except for the starting values of applying the recursion relations, that proves that the matrix elements are the Clebsch-Gordon. They are the Clebsch-Gordon coefficients to within a multiplicative factor, which is the starting value. Okay, that's as much as I want to do on proving the Wigner-Eckart theorem in lecture. There's more detailed and lengthier proofs that are given in the lecture notes, which you can read if you want to. I won't hold you responsible for them. And if you ever take a course in group theory, pay attention to Schur's lemma. It's a really beautiful result. And many of the things that I'm doing here are actually special cases of Schur's lemma. Okay, that's all I want to say about the Wigner-Eckart theorem. Are there any questions about this?
In the reduced matrix element, the double bars, do they mean anything in particular, or is that just the notation we've chosen for?
It's a standard notation, although it's actually, I think it's good notation because it shows you that what you're really doing there is you're getting the essence of what's left over after you throw away all the magnetic quantum numbers.
But that wouldn't be, so that couldn't be represented as like an integral over.
Yeah, so that's an interesting question. I think in more abstract points of view on this, one starts talking about vector spaces and vector spaces or quotients and so on. And I think there is an interpretation in which that can be done. So in other words, by suppressing the magnetic quantum numbers, that in a sense what we're talking about is irreducible subspaces. So instead of taking scalar products of vectors in spaces, we're taking scalar products of subspaces. And I think there's a way to make sense of that. I can't tell you the details, but I think, yes, that there is some notion in which that's true.
Okay.
All right.
Thank you.
Okay. And that leads me to the next subject, which is namely parity. Let's talk about parity in the next few minutes we have left. Parity is an improper rotation. By finishing the Wigner-Eckart theorem, I've finished everything I want to say about proper rotations, which has taken at least 2 weeks, if not more. It's much simpler to deal with parity, but we've got the hard part out of the way. But now let's worry about improper rotations. So to speak of parity, let me introduce a particular improper rotation I'll call P, which is just -1s in the diagonal and 0s in the off diagonal. It's otherwise minus the identity operation. This, of course, maps a vector into minus itself. When we give it a name, we call it spatial inversion. I think it's pretty obvious what it does. It's a mapping that acts on three-dimensional space and takes points into other points, flipping things through the origin. Now, we've been talking about the proper rotation group SO3. We can think of this as a set of points. I'll make it as a blob here, and somewhere in here is the identity. If we include the improper rotations, there's another blob containing improper rotations, and somewhere in there is the matrix P. The set of proper rotations, as I just indicated, is SO3. The set of improper rotations is not a group. However, the P matrix maps you from one to the other. If I take any matrix over here and multiply by P, it turns, which is really just multiplying by -1, it turns into a proper rotation and vice versa. So you can bounce back and forth between these two sets just by multiplying by -1. The two sets taken together is the full rotation group O3. Now, when we were dealing with just SO3, what we did was we looked for an association between elements of SO3, and we wanted to map them into operators acting on our state space we called U of R. They were supposed to satisfy certain properties, among which was they were supposed to reproduce the multiplication law. So now what we'd like to do is to extend that logic to include P as well. Before I get into that, however, let's see how extending the rotation group by adding P, let's see how it changes things. There's a new multiplication law because there's more elements now, you see. So what are some things we can say about it? Well, one thing we can say is that P squared is equal to the identity because -1 squared is +1. Another thing we can say is that P commutes with any proper rotation. PRP -1 is equal to R. if you take any, R here stands for a proper rotation. Let me just indicate here, this is proper. For any proper rotation, if you conjugate by spatial inversion, you just reproduce it. This is really a trivial identity because P is equal to minus the identity matrix. So you're just multiplying by -1 twice, and it doesn't matter which side you do. But in any case, as far as the multiplication law of the group, how it enlarges when you include improper rotations, this basically summarizes it here. All right. Now then, to go back to our quantum system where we seek operators that represent the classical symmetry operations. We've done this for proper rotations. What we need to do now is to generalize this to include P. We want a mapping that takes P into a U of P, an operator that acts on our state space of the system, which represents the effect at the classical level of spatial inversion. And we will call this operator pi to give it a name, or to give it a symbol, and we'll give it a name, we call it parity. So parity is the operator that implements the effect of spatial inversion. Now, what is the parity operator? Well, it depends on the system, just like the rotation operators did. So what do we require of the parity operator? Well, the requirements are the following. First of all, we require that it be unitary. Pi dagger pi is equal to 1 because symmetry operators are supposed to preserve probabilities. The second is that we should reproduce the multiplication law. So pi squared should equal the identity. That's the P squared equals identity. And the third one is that pi times the U of R times a pi dagger should equal to U of R for all proper R. All right, these are basically postulates that the parity operator needs to satisfy. Okay. Now then, this third property is interesting because if you rearrange it slightly, what it says is, it says that if I, instead of conjugating the U, I conjugate the pi, it says that U of R times pi times U of R inverse, U of R dagger is equal to pi. I get that, you see, if I multiply on the right by pi, here I get U of R times pi, and on the left-hand side, the pi kills the pi dagger, and I get pi U of R. Bring this pi over the other side. Then cancel the U of R by multiplying by UR dagger, and you get this formula here. So what this says is that pi is a scalar operator. As you see, it commutes with all rotations. All right, in any case, it's worthwhile noting that. And in particular, it commutes with infinitesimal rotations. So that means that the generator of proper rotations commutes with pi. This is a basic property which parity must have in all systems in which it is implemented. It has to commute with angular momentum. All right. Now, so those are the properties that the parity operator is to satisfy. What is the parity operator in various systems? Let's take the case of a spinless particle moving in 3 dimensions in which the Ket space is isomorphic to wave function psi of x, or if you prefer, it's the span of the basis states, which are the position eigenstates x, like this. In that case, you may remember that we guessed the definition of U of R for proper rotations is that U of R acting in the basis Kets was just another basis Ket at the rotated position. Well, let's just do this. Let's do the same thing. Let's guess again. This is really a guess now. But let's guess that U of P acting on x, which is the same thing as pi acting on x, should be equal to the Ket of px, which is the same thing as the Ket at minus x. This is to summarize, pi of x is equal to minus x. It's an obvious formula. And so let's take this as a guess for the parity operator for spinless particles moving in 3D. If we do this, then it's easy to show that the effect on a wave function is that psi of x is mapped by parity into psi of minus x, which is probably how you learned the definition of parity in your earlier courses. Now then, the question then is, does this definition of parity satisfy these postulates given above? It's easy to show that it's unitary because the integral of the square of the wave function doesn't change if x goes to minus x. So 1 is easy. pi squared equals 1 is easy too, because changing the sign in x twice just takes you back to where you started from. And this is easy also because the u of r, as I've just given you, here's what u of r does. So you change signs twice. And under this conjugation, you find you reproduce u of r again. So this definition, this guess definition for parity for spinless particles moving in 3 dimensions satisfies all the postulates that we laid out for it. And therefore, we will take this as the definition of the parity operator for those systems. So that's all for tonight. We're out of time. I will stop now and ask if there's any questions about this brief introduction to parity. You see, what's really going on here is we're just extending what we did earlier for the proper rotations as a rather large group of symmetry operations, and just adding one more operation, parity, to the mix. Now, that by multiplying parity times proper rotations, you get a whole lot of others. But if you just take care of parity itself by the multiplication law, you know what they all do. So it's really just defining that the one operator takes care of extending the group from SO3 into the full group O3. Later on in the course, maybe next semester, we'll extend that into Lorentz transformations. That's another extension one can make. So any questions then? All right, if there's no questions, we covered a lot of territory tonight. Let me stop screen share. One last chance before I stop the video recording for questions.
Oh, actually, can I ask a question about the previous lecture? There was something.
Yes, of course.
So when you were talking about like invariant irreducible subspaces of operators.
Yes.
And I was reading through the notes a little bit, and I came across invariant irreducible subspace of states as well.
Yes.
So then I was wondering if there's a correlation between if there's a invariant irreducible subspace of operators, and if there's and maybe their eigenstates, if they happen to be.
So the idea of an invariant subspace applies whenever you have a group acting on a vector space. So an invariant subspace is just a collection of vectors. You know, it's really just a subspace. You know, it's spanned by some vectors, but it means that any vector in the space is mapped into another vector in the same space by the operations. So that's an invariant space. An invariant irreducible space means that it doesn't have any subspaces that are also invariant. So it's invariant by itself, but it doesn't have any smaller invariant subspace. If a subspace is reducible, then you can break it up. And in this theory, they always turn out to be orthogonal subspaces. You can break it up into smaller subspaces, which are also invariant. Now, those smaller subspaces may or may not be irreducible. If they're reducible, you can break them into smaller spaces. But eventually, you're going to come to spaces that are irreducible. So that any original invariant subspace can always be decomposed into its irreducible components, which it turns out are orthogonal to one another. So that's the idea. So that applies not only to state vectors, but it applies to operators.
I see.
It applies to any vector space that the rotations act on. You could apply it to classical electromagnetic fields. If you take like electrostatics, so you've got an electric field produced by a charge distribution. Really, let's talk about the potential. It's easier. You have potentials produced by the charge distribution. You can rotate the potentials. It's just like a wave function. So you can break that up into irreducible subspaces under rotations. And this is connected with a multipole expansion of the field at large distances, you know, the monopole, dipole, quadrupole, and so on. Those are various subspaces that transform in that are invariant under rotations, and in fact are irreducible under rotations as well.
Mm-hmm.
So the notion can be applied to many different physical applications. The basic idea about, you know, being invariant and irreducible is the same. It's really just linear algebra.
So I was wondering about whether I understand the concept now of like it being invariant irreducible subspace that applies to states and operators. But then I was wondering if there's a relationship between if there's a subspace of operators and and if there's and maybe their eigenfunctions or their eigenstates, if
Well,
they form
the irreducible subspace of vectors is the way we've constructed them is they're eigenstates of j squared and jz, and you basically just let the magnetic quantum number run over its range. That's all it is. So an irreducible subspace of vectors is really just the basis vectors in which you allow m to vary and hold everything else fixed. That gives it a dimension of 2j plus 1. So their eigenstates are j squared and jz.
right.
Now, there's actually something analogous in the case of irreducible tensor operators, and I gave the formulas for it actually up here above. Instead of being eigenstates of j squared and jz, they form commutation relations with j squared and jz. Oh, I'm sorry, I don't have the screen share on anymore, but it's the commutation relations with j squared and jz that take the place of it. This will become more clear after a certain homework problem, which is probably going to happen next week. So if you're still confused about it, ask me then.
Okay, sure.
Good. Are there any other questions?
Yeah, really quick, can you just like give a quick overview of what what is the correspondence between like multipole and monopole and quadrupole subspaces to like here, like what? I'm just trying to understand, like we derived these subspaces for like angular momentum values. How does that correspond to the monopole and quadrupole moments?
You mean like in electrostatics?
Yeah, sure.
Yeah, so in electrostatics, if you think about the monopole term, it's rotationally invariant. So if you expand the angular dependence, it's a y00 is all.
Oh,
it is.
yeah.
Yeah, so that's where it is.
Ah,
In
yeah,
fact,
that's right.
in fact, it's really the same as just quantum wave functions of a spinless particle. I mean,
Yeah.
it's a scalar field. It's not complex, it's real, but that's what it is.
Yeah, it's literally just the harmonics. Yeah, okay.
That's literally all it is. If you look on books on E&M, they do a pretty good job of this on electrostatics because it's a scalar field for the potential. It makes it pretty easy to do. Then they talk about magnetic fields and they say, well, we don't have any monopole, we have a dipole term, and we'll just work that out. So you get the magnetic dipole term. Now the vector potential has got a non-trivial YLMs on it, you know, and they don't do the quadrupoles because it's too complicated.
Yeah.
Except Jackson kind of goes into it. And then to make it more complicated, if you want to talk about time-dependent electromagnetic fields, which is important in radiation, antenna theory, and all the rest of it, then you need what's called the vector spherical harmonics. And again, one is arranging them by irreducible they're not tensors, they're irreducible subspaces of fields, but now they're electromagnetic fields, they're vector fields. So there's a chapter in the end of Jackson's book, which is, in my opinion, kind of a miserable chapter to slog through. But what he's really doing is constructing the invariant irreducible subspaces of the electromagnetic fields that are radiated by antennas.
I see. So in this case, the space is like the space of vector fields. So it's like a Hilbert space of vector fields, right? Something like that.
It's not a Hilbert space, but it is a vector space, yes.
Oh, okay. Vector space of the vector fields.
Yep,
So there's
yep.
like a vector space of these functions. So then
It is a vector space
functions.
because you can add electromagnetic fields.
Got it.
Yep.
Thanks.
You can, by the way, this is a big deal if you ever do gravitational theory, general relativity, it's a very big deal there too. I mean, especially recently with the detection of gravitational radiation. So to understand gravitational radiation, you really need to know about all this stuff. Gravity waves, it turns out, don't have any k equals 0, and they don't have any k equals 1 either. They start with k equals 2, the quadrupole term. And so that's an important aspect, and you can't understand that without knowing this kind of stuff.
Cool. Thanks.
All right. Okay, anything else? Good, I'm so glad to get some good questions. And I'm going to stop the recording.